In this study, we present prototype systems specifically designed for computational notebook to enhance navigation and comparison performance. Computational notebook tools have become essential in data science, such as Jupyter Notebook, Observable, and Carbide Alpha. However, as data analysis grows in complexity, the standard computational notebook user's interface shows limitations in supporting complex tasks. Specifically, navigating through the extensive notebooks become increasingly challenging, complicating tasks like identifying issues in the analytical pipeline or refactoring the code. Immersive analytics were proposed to allow data analysis in VR and AR environments and successfully enhance performance in navigation and comparison. However, it is still unclear whether an immersive environment for a computational notebook may help with the data analysis. Another drawback of computational notebook is their linear structure. Imagine we are working on a complex data analysis task. The notebook keeps growing, becoming harder to manage. Now, let's say we want to test different values. If we found ourselves endlessly scrolling up and down to compare the results, it becomes a tedious and cumbersome process. Ultimately, navigating a lengthy notebook to find the optimal value becomes an unpredictable journey which limits the efficiency. To further enhance the data analysis performance, we introduced a feature called Branch&Merge. And here is how it works. Let's say we start with 5 windows in our notebook. To test multiple hypotheses, user can copy specific windows, creating a branch to assign different parameter values. A new kernel will be created and assigned to these newly copied windows and will be updated into other windows. Similarly, another branch can be created and its kernel will be updated with the same logic. And lastly, it is even possible to create another branch from a different window. In this case, a combined kernel will be generated from the previous branches. This means that the results will include 6 different outputs, each corresponding to the specific values assigned in each kernel. To test the effectiveness of immersive environments and branch-and-merge feature, we investigated the effect of computing environments and comparison methods. And here is our conducted user study. We collected 20 participants from university. All of them had experience with computational notebooks and data science. Next, we tested with 4 conditions: desktop linear, desktop branch, VR linear, and VR branch. In desktop condition, they needed to navigate using mouse, but in VR environments, they needed to use body movement to navigate and interact. And in linear condition, they were not allowed to create branches, which indicate that they need to stick with linear layout of traditional computational notebook settings. Where in branch conditions, we allow to create branches for more effective comparisons. Specifically in VR conditions, we employed gestural interactions. For example, users need to grab and pull out, or throw it away, or split it apart to perform following operations. Next, in each conditions, we ask participants to perform 2 different tasks, navigation and comparison. For navigation tasks, to access the performance across different types of navigation, we designed tasks that involved identification of specific cells, such as cells that makes an header. Then we introduce comparison tasks after navigation task, designed to simulate real-world hypothesis testing. Participants evaluated 2 parameters within various analytical methods to determine the optimal parameter combinations based on the visualized results. Here, we have an example of entire process of finding optimal values from DB-scan algorithm in VR branch conditions. We have cells displayed across multiple windows that are in a semicircular layout. We can select the cells and can be run by clicking the execute button on the left hand. Then all the cells that are in the lower hierarchy will be executed automatically. However, the graph in the last window is empty, which means that there is an error in previous window. To delete the cell, we first need to select it, grab it, and throw it away. Since it's deleted, we should be able to see the results at the last window. And we also need to relocate the specific cell into correct position. To do this, we first need to select the cell, grab it, and drag it over to the desired position, and finally release it. And lastly, we can also extract the cell by selecting it, grab it, and release it in the air. Next step is about creating branches. To do this, we first need to grab the window by both hands and split apart, then target window will be duplicated. Then we can test with multiple different hypotheses. For example, 3, 4, and lastly 5 at the last window. After finish assigning values, when we execute it, the merge results will be show up. If the results are too small, we can also make it bigger. And for more complex testing, we could test with another parameter values. To do this, we can create another branch at another window. And here we can assign parameter value with 4, and we can execute it. By doing this, we can see all the results at once in one window, which provides effective comparison. With those features and study, we could answer these two valuable questions. Is VR beneficial, and is branch and merge beneficial? First of all, we found that for navigation tasks, VR shows improved navigation performance. For example, we intentionally included codes that makes an error, where participants were required to identify and delete it. In this process, users were required to navigate through Computational Notebook. In the VR environment, this often involved head rotation, whereas in the desktop environment, mouse scrolling was performed. Our data suggests that physical interaction, such as rotating our head, is more efficient than employing a mouse for navigating expansive information spaces that exceed display size. However, when accessing comparison tasks, VR conditions tended to be slower. To systematically understand this observation, we analyze the duration on text input interaction across all task conditions. In our observation, we noted that participants spent considerable amount of time on text input within the VR environment, despite our efforts to streamline and enhance the text input experience. We believe this is due to the time spent on text input. However, we found that VR was faster after accounting for text input. Therefore, we identified that utilizing branch to compare multiple hypotheses in VR is partially beneficial. In summary, for navigation, we found that VR outperformed desktop within computational notebooks, largely attributed to its accelerated browsing speed and enhanced spatial awareness and memory. And for comparison, VR maintained its navigational advantage as navigation remains a crucial element in this task. However, the system's inefficiency in text input negatively impacted its overall performance. Additionally, although the embodied gesture interface in VR enhances user experience, it comes at the cost of increased task completion time. Next, branch and merge. We found that branch and merge shows faster completion time and fewer number of execution. Additionally, participants show that branch feature, the last two rows in the graph, indicates that positive in terms of mental demand, engagement, and effectiveness. And as well as user consider as VR branch as the most preferred condition to perform tasks. Lastly, we also noted that both VR and branch and merge feature was beneficial in navigation. For example, we found that from analysis of both navigation and comparison tasks, branch lowers the navigation cost in both desktop and VR condition. In summary, we could answer the question, is branch and merge beneficial? The answer we found is yes. We found that the introduction of branch feature considerably shortened the completion time for comparison tasks in both VR and desktop. To conclude, the branch and merge feature enhances the comparison process. Additionally, layout strategies. To better understand how participants use the given display space, we analyze the final layouts of each trial to understand strategies in desktop and VR settings. We observe only a few participants move their notebook windows from initial layout in a linear conditions. In contrast, the branch condition resulted in a wider range of layout strategies, especially in terms of the placement of newly created branching windows. Participants were favored of using in VR conditions since they have a lot more space to manage and place all those documents. Likewise, we present prototype systems for immersive computational notebooks designed with branch mechanism to enhance navigation and comparisons. We consider our exploration of performing computational notebooks in VR also provides concrete evidence toward enabling an iterative and fully immersive data science workflow. For more details, please refer to the paper. Thank you for watching.